With all the groundwork laid in place, in this video we'll start talking about isolated singularities. So first let's say the definition of what an isolated singularity is. So an analytic function f has an isolated singularity at z0 if f is analytic in the punctured disk, and this is a punctured disk. It's going to be modulus z minus z0 is less than r but greater than 0, where r is a positive number. So as always, we should draw a graph to make sure we know what we're talking about. So here's a small graph, and let's just say we're going to center this at z0. Let's say that's here. And then we want to pick a disk, so it's going to be an open disk, right? And it's going to have radius r. So what this says, an isolated singularity at z0 means that inside this disk, except at the point z0, so we choose everything inside this disk except the actual point z0, f is analytic there. But at z0, we're not sure. There's some confusion. Maybe the denominator zeroes out or something like that. In that case, z0 is an isolated singularity because we're not sure what happens there. Okay, so that's the basic idea, and let's go into two different types of them that we'll be using later on. So the first kind is called removable singularities, and they're called removable because we can kind of just take them out and pretend like they don't exist if we go through this process. So in pink I've written when this happens when the modulus of f of z remains bounded as z approaches z0. So again, let's start a little bit bigger picture just so we can get a better idea. So here's that open disk again. Of course, centered at z0, where we don't know what's going on, but we know everywhere else in the open disk, f of z is analytic. Okay, so what happens? The modulus of f of z remains bounded as z approaches z0. So as we're getting close to z0, let me put it in red. So as we get close to z0, basically from any direction, f of z is not going to infinity. It's not getting huge and huge and huge. So the modulus of f of z is remaining bounded. It's just staying under some number, not going off to infinity. So now let's set out trying to remove this singularity and pretend like it doesn't exist. So this is the process we're going to use. We're going to define a new function called g of z, and we're going to define this piecewise. So it's going to be the quantity z minus z0 squared times f of z, as long as you pick a z that's inside the disk but not at z0. If you pick a z as z0, then g of z is going to be 0. So we have g of z0 is equal to 0, but g of any other z inside this disk is going to be given by this function right here. Okay, so what do we know? We know g is definitely analytic inside that disk except at z0. So for purposes of this video, we're going to be calling this the punctured disk. So the punctured disk is the whole disk minus z0, because it's kind of like you take the disk and you put a puncture in it at z0, so that's not included. So g is analytic in that punctured disk. So is it analytic at z0? Well, let's find out. To find if it's analytic at z0, we want to take the derivative and see if it exists. So this is the derivative of g at z0, right? Limit as z approaches z0 of g of z minus g of z0 over z minus z0. So let's see what that happens. Now g of z is this whole thing. G of z0 is going to be what? It's going to be 0. So this just goes away. And then g of z is this. Now this, if we divide that by z minus z0, then one of these factors of z minus z0 will go away. And we're just left with one factor of z minus z0 times f of z. And now what happens as z approaches z0? Well, what's going to happen to z minus z0? This is going to approach 0. And what's going to happen to f of z0? So that we set up here is that modulus f of z0 remains bounded, which means f of z also remains bounded. It doesn't go off to infinity or negative infinity or anything like that. So since this remains bounded and this goes to 0, something bounded times something that goes to 0 equals 0. So we said since modulus f of z is bounded. So what we found is that the derivative of g of z at z0 is equal to 0. It does exist. So what we know now is something even better. We know that g of z is analytic for z minus z0 modulus is less than r. That's the whole disk, not the punctured disk, just everything, even including z0. So it has a power series in this disk. Remember we said in previous videos, we said if it's analytic in the disk, it has a power series in the disk. So we can write a generic power series, g of z equals b0 plus b1, z minus z0, and so on. So these are all coefficients right here. This one, this one, this one, and so on. But what do we know about the first two coefficients? What do we know about g of z0? So let's plug z0 into here. All these vanish because z minus z0 is 0, and we're just left with b0. So b0 equals g of z0, which is equal to 0, as we said from the definition of z0. So b0 is equal to 0. Now, what do we know about b1? Well, what do we know about that? What's g prime of z0? So what's the derivative of g at z0? Well, we said that was also 0, right? And if we take the derivative of this power series, we're just going to get b1. So that means b1 is also equal to 0. So this also goes away, this whole term right here. So we can make a more concise definition. We can start at b2 because these both terms are both 0. So g of z equals b2 times z minus z0 squared. We're starting at the squared terms, which is why we started at squared for the definition of of g of z, what we have here, why we have a square right there. So now what we can do is, since f of z is just g of z over z minus z naught squared, we can take this whole power series and just divide it by z minus z naught squared. So that's perfect, because then this term goes away, this term becomes put the power of 1, and so on. So we're left with b2 plus b3 times z minus z naught plus b4 times z minus z naught squared, and so on like that. And this is all true for what? It's true for this punctured disk. And is it also true for the whole disk? Well, it can be if we go ahead and just do the natural thing and we define f of z naught as b2. Because if we plug z naught into here, then all of these terms right here cancel out, and we're just left with b2. So we're going to say f of z naught equals b2. So now we know that f of z is analytic inside this whole disk. We know this power series is valid for the entirety of the disk right here. So what we have done, what I wrote here, we have successfully extended f to be analytic for the whole disk, and by doing that we remove the singularity, because by putting it analytic for the whole disk, it's as if that singularity doesn't even exist. So in this case, we say z naught is a removable singularity. And usually how you'll see this is if you have f of z is some function like z minus z naught squared over z minus z naught. And you might have run across this in calculus where you can just cancel one off both of them, and then you can have it be analytic for all z's in the disk, for example. But that's usually the form you're going to see it in. So the next type of isolated singularity we'll talk about is something that's going to be more important to us, called poles. So a pole, first of all, we'll see when it happens. This is what happens when it's not bounded. So it happens when the limit as z approaches z naught of modulus f of z is infinity. So what does that mean? Let's again draw a picture. So here's our z naught, and I'm going to draw, here's our disk. Now in the previous part, in the removable singularity, as we approach z naught from any direction, our modulus f of z remained bounded. It was not going off to infinity. But in this case, it does just that. As we approach it, it gets the f of everything close to the z naught goes off to infinity. The modulus just goes off to infinity. So what do we do in this case? So in this case, we're going to follow a slightly different process. First thing we're going to do is we're going to assume this r, this radius of our disk, is so small that modulus f of z is greater than 1. And why can we do that? Well, there's going to be an r, there's going to be some radius small enough so that everything inside there, when you take f of everything inside there, it's going to be bigger than 1. The modulus of it is going to be bigger than 1. And we can do that since as you get closer, the modulus is going to infinity. So there's going to be some r where the modulus of everything inside that disk is greater than 1. Okay, so, and we say that's true for this punctured disk, of course not including z naught, because we don't know what happens there. So now we're going to define a new function g. So our g in this case is going to be g of z equals 1 over f of z. So it's going to be the inverse, reciprocal rather, and it's going to be, this is going to be analytic on this punctured disk as well. And furthermore, g of z is bounded, right? The modulus of g of z is bounded because since the modulus of f of z is greater than 1 and g of z is just 1 over f of z, modulus of g of z is less than 1, just the opposite inside that punctured disk. Okay, so now what do we know? We can go back to removable singularities, and since modulus g of z is bounded in this disk, we have a removable singularity for g of z, so not f of z yet. We're going to connect that in just a second. So that means z naught is a removable singularity, so removable singularity for g. Also, g of z naught equals 0. And why is that? Well, what is f of z naught? It's going to be, we don't know what it is, but it's getting close to infinity. And since g is 1 over f of z, it's going to be something like 1 over infinity, which is getting close to 0. So we can define g of z naught as 0. Okay, so we say g of z naught equals 0 since modulus f of z naught approaches infinity. Okay. So next thing we're going to do, we're going to say let m be the order of the 0 of g at z naught. So I put in parentheses here just an example to kind of solidify what that is. So usually with poles, you're going to see it in a case where when you plug in z naught here, the bottom is going to go to 0, so this is going to go to infinity. So here's an example. We have f of z equals 1 over z minus z naught to the power of 3. That means g of z, being 1 over this, is going to be the denominator, or z minus z naught to the power of 3. So if you go back to the order of a 0 video, just the previous part of the last video, you'll see that the order of the 0 z naught for this function right here is going to be 3. Usually you can just pull it off by looking at the exponent right here. So we're going to say m equals 3 in this case. So now we're going to define a new function h through this definition right here. We're going to say g of z equals z minus z naught to the power of m, whatever that 0's order was, times h of z. Now let's note a few things about h of z before we move on. H of z is analytic on the entire disk. And why is that? Well, what was our h of z in this case right here? So look at this example I put right here. H of z was just 1. So in that case, it's a constant. It doesn't have to be a constant, but the point is it's going to be something that causes the numerator not to be 0, which means that h of z is analytic on the entire disk because it's not going to be a 0 at z naught. So that's why I've written here h of z naught is not equal to 0. So it doesn't cause us any problems there. And it's analytic on the entire entire disk. So in this case, h of z was just 1 because it's just the numerator, which you see here, because if we have g of z and we divide it by z minus z naught to the power of 3, we're just going to be left with 1, which is going to be our h. So h of z is 1, which is definitely analytic on the whole disk. So in general, when you have a pole, h of z, which is usually the numerator, is going to be it's going to be analytic on the entire disk, even including the punctured hole z naught. Okay, so now we know about h. The important things to know is that analytic on the whole disk and h of z naught is not equal to 0. So now, what we can do, we say since g is not 0 on this punctured disk. How do we know g is not 0 on this punctured disk? Well, it goes back to this. We know f of z modulus is greater than 1 on this punctured disk, which we said that tells us that g of z modulus is less than 1. But it also tells us that g of z modulus is greater than 0. So we can write that here. We can write g of z modulus is less than 1, but also greater than 0. Why is it greater than 0? Because as long as you keep plugging in, since g of z equals 1 over f of z, you can get this f of z to get bigger and bigger and bigger and bigger as you approach z naught, and g of z will get very, 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 very small, but it will never be 0, because you can't have 1 over a finite number be 0. Okay, so it's going to get close to 0, but it's still going to be bounded within this range. So since g of z is always, it's never 0, and h of z is defined as follows, that means h of z can never be 0, because if you have something that's never 0 divided by something else that's never 0, notice that this is also never 0 on the punctured disk. So something that's not 0 divided by something that's not 0 can never be something that's 0. So h of z is also not 0. So what we write here, h is not 0 either on the punctured disk. So now we're going to define yet another function, last function to define, promise. We have big h of z is the 1 over small h of z. And this is analytic on z minus z naught to the, less than r. So it's analytic on the entire disk. And why is that? Well, it's analytic on the entire disk. It would not be analytic on the entire disk if the denominator causes any problems. But does it? No, because h is never 0. So no problems here. It's analytic on the entire disk. So now altogether, what do we have? We have f of z equals 1 over g of z. That's the first definition we made. We redefine g of z as z minus z naught to the power of m times h of z. So this is equal to this. And then we defined 1 over h as big H. So we just put that on the top, and we're left with z minus z naught on the bottom, to the power of m on the bottom. So all in all, f of z equals h of z over z minus z naught to the power of m. So what I've written in parentheses here is, again, just to remind us, h is analytic on z minus z naught less than r modulus, so it's analytic on the entire disk, and h of z naught is not equal to 0. Why is it not equal to 0? Well, because small h of z naught is not equal to 0, and big H is just 1 over small h, so it's not 0 either. So the final statement here is that, so f is an analytic function divided by z minus z naught to the power of m. And why is that true? F is an analytic function, so this is the analytic function right here, divided by z minus z naught to the power of m. So we can, whenever there's a pole, we can always write f as some analytic function divided by z minus z naught to the power of m. And that's the important thing. And if that's true, we can say f has a pole at z naught. And furthermore, you can say with order m. So we call the order of the pole m, which is the order of the 0 of g of z, as we saw right here. Okay? So the last thing we'll talk about is residue, which is going to lead us into the next videos and so on, because we're going to use it for residue theorem and lots of awesome stuff like that. So first, we're just going to consider something. Consider this kind of nasty looking integral. 1 over 2 pi I integral f of w dw over this circle centered at z naught with radius s. So this looks a lot like Cauchy's formula, which is good because that's kind of where it's from. So now what we're going to do, we're going to say if f is analytic in this disk right here. So we're going to have to, one condition for residues is that f has to be analytic in the punctured disk centered at z naught with radius r. And we're going to have s is a positive number, but smaller than r. So again, let's draw a picture just so we know what's going on. So here's our z naught again. And we said that f is analytic in the punctured disk. So here's a punctured disk. This whole blue disk right here will be a punctured disk. And we're going to say that this integral is taken over s, and s is a circle whose radius is smaller than this radius. So it's going to be still centered at z naught, but it's going to be something with radius smaller. So it's going to be this circle right here, for example. So what we want to prove is that this integral is the same no matter which circle we choose, which means we can choose that red circle I drew, or we can choose another circle, all the circles we draw have to be, of course, radius less than r, but we want to show that no matter which circle we choose, the integral should be the same. And how we're going to do that is this. Pretend we have two circles, one with radius s1, this is the smaller circle, one with radius s2, this is the bigger circle, okay? And of course, they both have to have radius smaller than r. So if I were to draw the radius circle r circle, it would be something like this. It would be on the outside, okay? So now we're going to let S1 is less than S2, but they're both less than R, and they're both greater than 0. Okay, so now we want to find the integral of f on the smaller circle, and we want to add it to the negative of the integral on the bigger circle. So what we're basically doing, we're taking the smaller circle with the positive orientation, and we're taking the bigger circle with the negative orientation. We're adding them together. And what we want to find is that they're equal to 0. So what we want is equal to 0. Because if they're equal to 0, then that means these both are equal to each other. And let's just do that right here, last thing. So this is a pretty clever way to do it. So these orange circles are the same circles on the other side of the paper. This one's the S1 circle, this one's the S2 circle. And what we're gonna do is we're gonna take 4 different integrals. So I've drawn purple integral, green, gray, blue integral, okay? What's the purple integral? So it's gonna be here. It's gonna start up here at this dot, go down this quarter of the circle, come across this line right here. It's going to go up this part of the smaller circle and go up this vertical line to meet its same point. What's the green circle? The green integral. The green integral will start right here. It'll go down this arc of the big circle, come up this line. So it's actually traveling on part of the axis, okay? And then it's going on the smaller circle, and then it's going back to where it started. And the same thing with the gray and the blue integral. They follow the same thing. Now, why did I make this so complicated? Well, the reason is because this complexity it actually reduces the complexity of the entire problem. Because what are each of these purple, green, gray, blue integrals? They're all closed loops, right? Because they all start and end at the same point. And by Cauchy's theorem, we know that if f is analytic, f is analytic for all these closed loops where all these closed loops lie. So since it's analytic where all these closed loops lie, that means the integral around these closed loops is equal to 0, which is what's important. So that means the purple integral is 0, the green one 0, gray one, blue one 0. Since they're all 0, add them together, it's still 0, correct? But what are these integrals also? Note something important. So remember we traveled across these parts of the axes. We traveled across this little segment right here, this segment here, this segment here, this segment here. In fact, let me draw this one further so we can make sure it's consistent. So let's look at this segment right here. So I'll put it in right here. So this segment right here, we traveled across it in the leftward direction in the purple integral, but we traveled in the rightward direction in the green integral. So since we traveled across it 2 times in opposite directions, it cancels out. That's how line integrals work, if we remember. So let's do it for one more. Let's look at this segment right here. We traveled across it once upward in the purple integral and downward once in the blue integral. Since we did that, once upward, once downward, it cancels out. In fact, all these segments cancel out. So what are we really left with? We're just left with the circular arcs. So we're just left with the outside integral taken with negative orientation plus the inside integral with positive orientation. So that's what we're left with. The inside with positive minus the outside with negative orientation. And that's exactly what these 4 integrals add up to. And also they add up to 0. Since they're 0, that means this integral right here, this integral, equals this integral. And what's the only difference between these two? It's the radius that we chose to put it around. So what does that tell us? That tells us that this integral right here, 1 over 2 pi I, integral f of w dw, with centered at z0 with radius s, is independent of the choice of s, does not matter at all. So since it doesn't matter, we're going to call this seemingly, right now it probably seems weird while we're even talking about this, but I promise it'll become clear in the next and future videos. We're going to call this quantity, which I've underlined in green, the residue of f at z0. And we're going to put a short form as, you can write res, res, in parentheses f, and you can put a semicolon z0, and that's going to be the residue of f at z0. So we'll see why this is important in future videos, and I promise it's very, very important to calculate integrals and stuff like that.